Welcome back to the session. So we'll just go ahead and we'll start with today's session on the live problem solving sessions for NPTEL. So I'm Prithvi. I'm a PhD scholar from IIT Hyderabad. So in the last week we were discussing about the energy methods. With the help of energy methods, we are trying to solve the indeterminate structures using the energy methods, and we tried to use the flexibility method. So flexibility method, usually we use the compatibility conditions to solve the unknown reactions. So in the last week we tried solving some indeterminate beams and as well as indeterminate frames. So in this week, we will try to solve the same indeterminate structures, uh, and there are many theories, or many different types, or uh, many different what do you say different types of solving the indeterminate structures, because again, as we say the term indeterminate, that means we in addition to the equilibrium conditions, we also need additional extra different other conditions to solve this indeterminate structure. So we try to use the compatibility equations in addition to the equilibrium equations to solve these structures. So again, the slope deflection equations, these are also famous equations. The almost, I think it was proposed, or it was theorized in around 1920s or 1910s. So this is actually in a very refined way, G.A. Mane developed these equations. So let us solve. Let us before we solve the before we solve some questions on the slope deflection problem. So let us try to understand the concepts behind it. We'll quickly go. I know that you already have gone through the video lectures, but just for the sake of for the sake of completeness, I'll try to quickly generate, or quickly try to solve some concepts behind the slope deflection, how it has evolved, and what are the basic steps involved to actually derive the slope deflection equations. So let us start. Let us move ahead. So let us suppose a beam. There's a beam. It's a continuous beam. So the reason why I'm taking a continuous beam, because again we wanted to have a have an approach to solve the indeterminate structures, right? So continuous beams are indeterminate beams, right? So we have a continuous beam, something like that, and it has let us say it was loaded with some load W. This is W, and it also has some, let us say, point load P acting at some distance. So let us say the beam is the spans are like length of the span is L, and let me name this support as A and this support as B. So the first step, it is an indeterminate structure. You assume it as an indeterminate structure. It is a continuous span. I have taken only the mid span to just derive the slope deflection equations here, and also some assumptions. I think the same assumptions has been considered in the lecture. So I'll take clockwise as positive moments now. So clockwise is positive, and in this we also include support settlements. Okay, so in formulation, so it is much easier for us to actually have support settlements, so that again we don't need an extra step to include support settlements in the further analysis. So what I'll do is I'll take delta is support settlement. Support settlement is nothing but the support settling down. Okay, maybe due to the maybe it may be any reason. The beam which is sitting, or the column which is sitting, or the foundation which the beam was sitting on. Maybe the soil is too weak to hold it, and it has settled down, or it has consolidated down to actually account for some support settlement. So let us say delta is my support settlement, and I'll take downwards as positive. If my support is settling down, I'll take it as positive. And yeah, that's it. So if my movement's clockwise, it's positive. Then if my theta, which is actually uh, the slope, right? The slope of the beam, that is also clockwise positive. So now I'll just take this part of my beam. So what happens? So we have a, and what happens to this beam is, so let us say it has moved. Yeah. So let us say the support has settled, and the beam has deflected something like this. So this is how the beam has deflected down. So this is my delta, which is support settlement. We also have, this is my theta A, and let us say this is my theta B. Okay. So okay, for just time being, let me assume that my theta B is also in clockwise direction. So the theta B is also in clockwise direction. So this is my theta B. And what else do we have? We have a chord also, right? What is chord? Chord is actually, see, what we assume is the beam bends, and the beam actually is a part of an arc, right? It's an arc. So just join A and B. It's a straight line, that is called a chord. So this is my chord. So yeah, so these are the things which we try to find out, right, to find the slope deflection equations. So for that, what I start assuming is, so let us say this is my support A. So support B is actually having a fixity, right? So it is actually continuous beam, but you always have the reaction, the movements which the continuous beam takes is, it takes MBA. The BA will have some moment, and also MBC will have some moment. MBA plus MBC should be zero. So that is what the condition is. So when a theta A rotates, like when my support A rotates, what happens? So my support A is rotating something like this. So because of my support A rotation, what is my MA? So this is my, I write it as MAB, and this is my MBA. Okay. The length is L. This is theta A. All right. So again, this is an indeterminate beam. So we'll make use of conjugate beam method to find out what is theta. See, in this actually what we are trying to find out is, if I apply a moment MAB, and if it is inducing theta A as the rotation, and I have a fixed support at the other end, which is B. So the other end is B. So I wanted to find how much movement I should apply. Okay, how much movement I should apply, or what is my theta if I apply MAB, if the end support is B. Okay, we need to find the moment MAB here. So this itself is this is like a prop cantilever. I don't think we can call it as a prop cantilever. It is we have a simple support, and we have a pin support at one end, and we have a fixed support at the other end. So I'll try to make use of conjugate beam method here. Okay. So in a conjugate beam, the pin support will be as a pin support itself, whereas the fixed support will be a free end, right? So at A now, what I'll try to draw is, I'll try to draw a bending moment diagram. So this is MA. This is going to be MAB by EI. Similarly, at support B, we also have MBA coming up, right? So MBA is in again opposite direction. So this is how it is. So we have MBA and MBA by EI, and you assume similar triangular. So there is no forces in between within the span. So that is the reason why I haven't considered any a moment because of this force. We only have end moments, right? MAB and MBA are the end moments. And MAB, I'm applying, and MBA is actually because of MAB which I'm applying. Okay. So because of MAB, I'm having a rotation of theta A. All right. So again, I'll label this as A dash, and this is B dash. Now again, just we'll recall what is happening in a conjugate beam. If we want to find the slope in the actual beam, the slope in the actual beam is equal to the shear force in the conjugate beam. So right now I want to find theta A in the actual beam. So for the conjugate beam, I should actually evaluate my theta. My Just a second, someone just joined. Yeah. So in a conjugate beam, what I'll try to evaluate is, if I want to find theta in the actual beam, I will try to evaluate shear force in the conjugate beam. So my VA will be my so let us say this is vertical reaction at VA dash. This is nothing but my theta A. Okay. So I need to find VA. So to find VA, what I can do is, I'll just so we have VA, and we also have another equation which is with let us say we have let me take moments about summation of moment about M A dash is equal to 0. So what I'll try to get is the loading. So now the bending moment diagram becomes the loading diagram, right? So it is half MAB by EI times L into L by 3 minus half MBA by EI times L to L by 3. Okay, so that should be equal to 0. Sum of moments about the support A should be 0. So this is my condition 1. What is my other condition? M B dash should be 0. Summation of moments at M B dash. M B dash is a free end, right? So at free end there should not be any moment except if there is some external moment coming out there. So in this case, what happens? Half MAB by EI into L. This is my area of the loading curve, and this is my centroid 2L by 3 minus half MBA by EI times L times L by 3. This is my centroid. Now we have this plus VA dash, right? So VA dash, I'm just writing it as theta A. Okay. So VA dash is nothing but the support reaction at A. So I'm just trying to write it as theta A. Theta A, support reaction in my conjugate beam is actually the deflection. Sorry, is actually the slope in the real beam or in the actual beam. So it is nothing but theta A times L, that should be 0. So we have two equations, and the two unknowns are MAB and MBA are my two unknowns, because what I've assumed is I'm applying a rotation of theta A. So I just want to find, to apply the rotation theta A at the simple support, where my far end, I call my support B as my far end, where my far end is fixed. Because of that, how much movement I should apply at A and how much movement is actually generated at B. So for this, what I'll have, my MAB and MBA are my unknowns, and the theta A is known. Two unknowns, two equations. So by solving this, solving the above equations, you can simply solve this. So EI will go to the right side. So EI, all the EI's can be go. We can actually shift it to right, else cancelled. And I'm just directly writing down what the answer is. So M A B should be 4EI by L times theta A, whereas MBA is 2EI by L times, sorry, theta A. This is not theta. Okay. So this is my first solution. So from this, what we are trying to understand is, let us say I have a cantilever, I have a beam. Okay, I have a beam AB, where my far end is B, and the uh, where my far end is B, and I want to apply a rotation of theta A at support A, because to apply the rotation theta A at support A, I need to apply moment MAB of 4EI by L theta A to actually have a rotation at A, and because of this moment MAB, I also have a moment generated in the far end support, which is MBA, and that is equal to 2A. That means it actually it actually transfers half of its moment to the far end support, that is MBA. Similarly, let us do for let us just do it for the other case, which is, now my A is fixed and end B is pinned. Okay, so I just want to do the same thing. So for again, I'm considering my clockwise as positive, right? So if clockwise as positive, this is how I'll rotate. This is my theta B, this is A, and this is B. So this is again similar, right? It is just symmetric, or it is just the mirror image of the first one. So in this case, what happens? MBA will be 4EI theta B by L, and because of this MBA, so you need to apply a moment of 4EI theta B by L to actually induce a slope of theta B in support B, and because of this moment, it transfers moment at A, because A is actually a fixed support, right? It has to resist moment also along with the shear force. So right now we are not bothered about the shear force. I'm only considering the moment, how much moment it is transferring to MAB, or how much is the moment transfer to the support A. So because of this moment applied MBA, the resistance at MAB is 2 times EI by L. Okay, this is one set of the equation. Similarly, we have again we also considered a displacement, right, which is the support settlement. So for delta support settlement, now similar case. So far we are discussing about rotation. So we have used shear force to find out the rotation in the conjugate beam. Now for the displacement, what we'll be using it, we'll just use the bending moment at that point to find out the displacement, right? So again, let us have the same beam. It's a fixed beam here. Fixed beam here. Okay. So there is a support settlement. Okay, you have a support settlement. Again, you need to mind this. So right, so far in my the previous question, I did not consider any delta there, right? So that is why I'm considering it as a pin, because I want to show there is some display, to show some slope at support A. So if I want to show this, there is some slope at support A, either I can show as a pin support, or I can also show it as a fixed support, but I can rotate my fixity there. Okay, but in my second example here, which is delta, in this I want to show exclusively only delta here. So that is the reason why I did not put any pin support there, because I have taken all my rotations in my in my first part, where I have used my pin support over there. So in this I want to only find out my support displacements, support settlements, which is actually inducing the forces in the beam. Okay, so this is delta. If this is delta, how much again movements will be there because of this delta support settlement? What are the movements transferred into the beam? Okay, that we need to find. So let us say this is MAB again. This is MBA. So this is the real beam, which is a fixed beam. Again, what happens if it is a fixed beam? if it is a fixed beam, the conjugate beam will be the free ends, right? Both are free ends. So this is my free end, and you need you. Anyways, you can also find out, but let me just draw. So this is MBA, and this is MAB. So this is my MBA, and this is my MAB. Now, one thing I think you need to understand here is there is no support in the beam, right? There is no support here because both are the fixed beams here, and the conjugate beam, the respective conjugate beam for the fixed beam is it's both sides are free, right? There is no support. So if there is no support, it has to self balance itself, right? So if it has to self balance itself, now you need to understand that MBA should be equal to MAB. Only then it can self balance, right? The upward forces should be equal to downward forces. So in this case, the equal moments will be transferred to both the supports MAB and MBA. So I'll just write it as M. So MBA is equal to MAB, and in this case, the delta is known. The delta is at B, support B. So what is delta in conjugate beam? If you want to find the displacement in the real beam, for the conjugate beam, the delta is nothing but the bending moment at the point of interest. So the bending moment at B is, I just want to just elaborately write what the bending moment equation, half M by EI in times L times 2 by 3 times L. This is my centroid, minus this is because of uh, the downwards loading, or the downwards force. So half M by EI times L times 1 by 3 times L. Now I also have that is equal to delta, but I'll take minus delta, should be 0. Okay. So this is going to be, in this I just want to find out my M. M is going to be minus 6EI by minus 6EI delta by L square. This is very famous equation actually. So M, if there is a support settlement in a fixed support, if the far end of the support is settled by delta displacement, it actually induces a minus EI 6EI delta by L square in both the supports. So this is M is nothing but minus EI delta by L square. So this is also MAB and MBA. Okay. So if it is settling down, so what you are going to get is you are going to get, see I have said clockwise positive, right? So it is going to generate anti-clockwise moments here. So this is MBA and this is MAB. So this MAB and MBA is going to be 6EI delta by L square anti-clockwise. So these are the equations so far which we have written. So from this so far, again we are again discussing about only the linear parts, right? Where my stress is equal to my stress is proportional to the strain, and there is a so this is always in the elastic limits. So my stress is directly proportional to the strain. So what happens if the stress is, why do we need to take care of it, or why is it so important when we talk about the elastic zones? Because what happens in the elastic zone is the superposition principle is always valid. So you can have multiple steps. For example, if you have 10 kilonewtons acting on the beam, you can actually break down into 1 kilonewton each, and you can add it 10 times to actually. So when we say it is a when we say it is the structure is within elastic limit, that means the superposition principle always valids. So in the same case, so far we have discussed about the rotation at one support and what is the moments induced because of that rotation. At the same time, we also discussed about the displacement at one support and what are the movements it is actually inducing because of the displacement. So what happens if there is both rotation and also the displacement? So we can actually simply add these two stuff together to actually find out what is happening, because in this we assume that the superposition principle is valid because the structure is in elastic limit. So what happens is that MAB, if I have both the rotation as well as the support settlements happening there. So MAB is, if you remember the first equation is What is it? MAB is 4EI theta A by L, 4EI theta A by L plus 2EI theta B by L minus 6EI delta by L square. This is my MAB. Similarly, MBA, we can write it as 4EI theta B by L plus 2EI theta A by L minus 6EI delta by L square. Okay, so you need to mind one point in this. So far we never discussed anything which is happening within the span, right? So we only said that there are some rotations happening at the supports, there is some support settlements in the supports. Okay, we never spoke anything about the loading which is within the span. We never we never taken the loading or the loading in the span as into we never consider the loading in the span. So what happens if there is some loading in the span? Let us say we have a fixed beam. So let us say this is my fixed beam. I have a UDL of W on this. So what is this going to induce? It is going to induce hogging moments of WL square by 12 and WL square by 12. Okay. Similarly, fixed beam, I have a point load acting at L by 2. Okay, and this is also going to induce my hogging moments, which is PL by 8 and PL by 8. Okay, so now let us just consolidate all these things. So instead of writing all these WL square by 12, I'll just simply say fixed end moments. Okay, fixed end moments AB, fixed end moments BA. Okay, so let us just I will just repeat what I've said earlier. So the beam is actually in the structural system, whatever we are considering, it is in the linear elastic zone, and we have superposition valid. So because of the superposition valid, we have actually break down this type of a problem into three different parts. One part where I have induced my rotations. Okay, where I have induced my rotations. Let us say, okay, now I'll just I'll try to consolidate graphically. So we have these rotations. There is, and also maybe there is some, okay, in this way. So I have my support has actually, so you have, this is my support and this is another support. So let us say I have some load coming here and this has bent in this fashion, and there is display support settlement of delta here, and you have, this is W. So first condition, we have considered that there is support rotations. Because of the support rotations theta A and theta B, what are the movements that is developed in the fixed supports. So MAB and MBA, we have already included that. Next, second one is we have also considered the support settlements. So because of the support settlements, what are the moments that has been induced, or that has been that has been induced in the beam, that we have considered that as again MAB MBA. We found it as 6EI delta by 6EI delta by L square. That is again in anti-clockwise direction if the support element downwards is taken as positive. And also we right now we have support rotations and support settlements. Now what if there is what if the span is carrying some loads W and L, or W and P, the UDLs and U, it can be anything, UDL or UVL, uniformly varying loads, and also the point loads P. So now what happens is this will be modified as the equation whatever we have written previously. This will be modified as plus, it will also have fixed end moments MAB because of the loads FEMBA. So this is my slope deflection equations. Okay, this is my slope deflection equation. So MAB is actually the moments in AB because of the support rotation theta A. Again, this can be interchangeable. If you want a support reaction theta A, you need to apply MAB. At the same time, if you are applying MAB, the theta A will be your support rotations. Okay. Again, this is because we actually considered this the direct or the proportion, the linear elastic concepts here, right? So that is the reason why we have the similar kind of MAB which is directly proportional to the theta A, or even the P and delta, that is also directly interchangeable. So MAB is equal to F 4EI theta A L by theta A by L by L plus 2EI theta B by L minus 6EI delta by L square plus fixed end moment AB and so on. So just let me write it like how the textbooks writes it. So this can be written as MAB is 2EI by L times 2 theta A plus theta B minus 3 delta by L plus fixed end moments AB, and MBA is nothing but again 2EI by L 2 theta B plus theta A minus 3 delta by L plus fixed moments in BA. So this is actually the standard format of what the slope deflection equations are. So once if we keep on using it, and with the help of compatibility conditions and with the help of the equilibrium conditions, we will try to use this to find out, again at the end of the whole and sole purpose of doing structural analysis is to find out the support reactions or the internal forces, right? The internal forces or the support reactions, because that is if we try to find them, it will be easier for us to understand what or estimate what are the loads coming, or what are the uh, obviously the outputs of the structural analysis is nothing but the inputs to the structural design, right? So with this MAB and MBA, we can actually find out what is happening in the structure by determining the support reactions and also the internal forces. So I'll directly go to the question. We'll try to solve it, and I think by solving the question, it will be very clear on how we use this slope deflection equations. So I'll take two questions. One question I'll take a beam problem, and second question it's not so complicated, but there is some uh, um, there is some additional stuff which we need to know in that. So that is the reason why I've also taken one problem on frame on frames. So we'll take two questions in this session. So our first question is a beam problem, and second question we'll also take up one problem on the frames. Uh, so let us solve this, and maybe after solving this question, we can wait for some time to solve if you have any questions. So first question, I have a fixed beam. I have a beam. So this is my roller support, and again I have a roller support here. So this is my beam ABC. So AB is having a UDL of 2 kilonewton per meter, and BC has a point load of 12 kilonewtons. Okay, and the spans are 24 meters, and this is 8 meters. Okay, so solve for support reactions, and again it's a very good practice to always draw bending moment diagram and shear force diagrams, how it is varying, so that we can easily we can try to finalize our designs at the end. So using slope deflection method, that is very obvious. So now this is my first this is the question. So how do we use the slope deflection method in this question? Again, we'll try to answer all those questions here. So First let us just we have this equation, right? We have this equation MAB is equal to 2 EI by L 2 theta A, theta B 3 delta by L. Yeah, please. Yeah, in this we don't have any support settlement. No support settlement. No support settlement. Anyways, if it is not given in the question, then there's no point of taking it. So 2 EI by L, 2 theta A plus theta B minus 3 delta by L plus FEM. FEM is fixed end moment, so FEM AB. So the sign conventions are very much important in this. We can't ignore this because the equation which is developed here, it is highly it has a very high weightage for the sign conventions, right? We have considered the signs in certain fashion, and we need to actually use the same conventions which we have used to derive this formula. So let me start. So in this C, we have again two parts. So previously we are discussing about AB part, right? In this we have AB and also BC. Okay, we have two beams where B is a common part or a common support. So let us first calculate FEM or the fixed end moments. So fixed end moments of AB. So for the fixed end moments of AB, so again in the slope deflection equation, initially what we'll assume is when we are finding out fixed end moments, right? We assume that all the supports are fixed ends. Okay, all the supports are fixed ends, and we will try to find out what are the fixed end moments. So FEM fixed end moments of AB is nothing but WL square by 12, and this is in this direction, right? So that means we need to take it as minus because clockwise is positive. That is what we have considered. So we have minus W is 2 kilonewton per meter and L is 24 square by 12, and this is 212. 2 4 times 9 24 is 96 minus 96 kilonewton meter. Okay. Now fixed end moment of BA, that is again, is it plus or minus? Yeah, this is plus because you have a positive moment coming here like this. So WL square by 12, that is going to be 96 kilonewton meter. Okay. And fixed end moments of BC. BC is nothing but minus PL by 8, that is minus 12 by 8 by 8, that is minus 12 kilonewton meter. What about uh, FEM of CB? This is PL by 8 positive because positive it is clockwise, something like this. So you may let us see again. Maybe you'll be having a lot of doubts because the C is not a fixed support, right? Why we are going to write FEM? We'll see what happens. So PL by 8, 12 times 8 by 8, that is 12 kilonewton meter. Okay. So if you remember what we have done in the formulating the slope deflection equation, what we have done is we have assumed everything as a fixed support, and then we have assumed that there are fixities, there is joint rotation or the support rotation, and there is joint settlements there, right? So we have found out if everything is a fixed support, what are the equations. So what happens if there is some pin there is a release, right? So that means MCB will be 0. That's it. So anyways, we can come to that a little bit later. So let me write down what are my equations for MAB. MAB, if you remember, it is 2 EI by L. For the first one, I'll just write down the entire formula. 2 EI by L, theta A plus theta B minus 3 delta by L plus FEM fixed end moments of AB. So this is going to be 2 EI by, okay, EI is the same. EI constant. 2 EI by L is 24. 2 theta A. So you might ask me again, if it is a fixed support, how do we have a theta? We'll see what happens. Theta A, it will be vanished. So 2 theta A plus theta B minus delta is 0 here because there is no support reaction. FEM AB is minus 96. Okay, so this will be EI by 2. What is this? Fine, let me directly write it down here itself. This is EI by 12 2 theta A plus theta B. I'll I'll consider it as equation 1. MBA is again EI by 12 2 theta B plus theta A. Again 3 delta, delta is 0. FEM, fixed end moment of BA, that is again plus 96. This is my equation 2. Let me also write down MBC. This is going to be EI by 2 EI by 8, that is 2 EI by 4, 2 theta B plus theta C minus 3 delta, delta is again 0. FEM is 12. You can see here it is 12. Okay, this is my equation 3. MCB is EI by 4, 2 theta C plus theta B. Again, delta is 0 plus 12. Okay. So now comes your I think now it's time to solve clear all the doubts. So MAB we have, MBA we have an equation, MBC we have an equation, MCB we have an equation. In this everything is unknown, right? We don't know what is MAB, we don't know what is MBA, MBC, MCB, we don't know. And also theta A, theta B, theta C, even that we don't know. So we have 4 plus 3, 7 7 unknowns in this, but we only have 3 equations, out of which again by inspection you can say theta A is 0 because it's a fixed support. Yeah, theta A is 0. So in this also theta A will vanish. That is one we so now we have uh, MAB, MBC, MCB, MBC, MCB, and theta B and theta C, theta B and theta C. So we have 6 unknowns, but we still have only 4 equations again. And also you should be knowing here C, support C is again a roller support. So what happens in the roller support? There is no external moment acting on the roller support now. So there is no moment there. So moment should be 0 at that roller support. So what is moment there? It is MCB. So MCB is also gone. So again I have MAB, MBA, MBC, theta B and theta C. So I have 5 unknowns. Again I have only 4 equations. So what shall we do in this? So in this we can again we can consider one. There is one more equation which is lying inside. Okay, it's again, if you actually just inspect this carefully, we can write one more equation which is MBA plus MBC is equal to 0. This is my 5th equation. How did I get this? This is very easy. So let us say this is my A, B, this is B, C. So whatever happens at BA, this is MBA, right? So it has to transfer MBC in opposite direction, right? Because it's again Newton's third law, right? So uh, uh, you have action which is coming, which is MBA, and it has to resist which is BC. MBC should resist the same force which is actually resisted by MBA. So MBA plus MBC should be 0. So this is my 5th equation. So I have 5 unknowns. I have 5 equations. So I can solve it very easily. So MAB. I'll just write down the equation. So now I'm just MAB. Yeah, MAB. MAB will be directly EI theta B by 12 minus 96. Okay. MAB. Yeah. So first let me just solve this. MBA plus MBC equal to 0. So MBA, what I have obtained, EI by 12 2 theta B plus 96. Is it what I'm obtaining? It's yeah. So MAB is EI by 12 theta B minus MAB is EI by 12 into 2, sorry, into theta B minus 96. MBA is MBA is EI by 6. Let us take EI by 12 itself. EI by 12 2 theta A plus 96. MBC is MBC. How much is MBC? EI by 4 2 theta B plus EI by 4 2 theta B plus theta C minus 12. MCB, which is 0, that is equal to EI by 4 2 theta C. EI by 4 2 theta C plus theta B plus 12, that is equal to 0. So from this, let us write down E 2 theta C plus theta B plus 12 equal to 0. Okay. So what happens? So let me just plus 12. It's not 12 plus 12. This is EI by 4 equal to 0. So theta B can be written as minus 48 by EI minus 2 theta C. This is theta B in terms of theta C. Now I also have MBA plus MBC. MBA plus MBC equal to 0. So where is MBA? MBA is EI by 12. So this is theta B. Sorry. So EI by 12 times 2 theta B. 2 theta B is again, how much is that? Minus 96 by EI. I'm using this equation, 96 by EI minus 4 theta C. Okay. Plus 96 plus MBA plus MBC. MBC is again EI by 4. EI by 4 times 2 theta B again minus 96 by EI minus 4 theta C plus theta C minus 12, that should be 0. So this will be further simplified as EI gets cancelled. 12 times 12 8 minus 8 minus 4 plus 496. So anyways, this all will be equated to theta C by 3 minus 3 EI theta C by 4, that is equal to 0. That implies theta C can be found as 48 by EI. Okay. This is again simple mathematics. You just take theta EI to the other side. That will be 52 by EI. So 1 by 3 plus 3 by 4 is again 12. You have 13 by 12. So 13 times 4. This is 48 by EI. So you have found out theta C. So you know theta C, then you can find theta B. What is theta B? Theta B is minus 48 by EI minus 2 times 48 by EI. This is going to be minus 96 plus 48 is minus 144 by EI. So this is my second one, which is theta B. Further, yeah. So theta B, theta C I have found. So what else do I need to find? Yeah, those are, yeah. Then I think it's done. So we have theta C, theta B, which is found. So we can find out MAB, MBA, MBC, and MCB. MCB is 0, obviously. So MAB, I will submit my theta B in MAB. MAB is EI by 12 theta B. EI by 12 theta B is minus 144 by EI minus 96. This is 12 squares. So EI goes off minus, this is 108 kilometer meter. Okay. So MBA, what is my MBA? EI by 12 again 2 theta B plus 96. EI by 12 2 times minus 144 by EI plus 96. So 12 again, 12 knocks off minus 24 plus 96. That is going to be minus 72. MBC. So by now I should be able to say this. So MBA plus MBC should be 0. So MBC should be 72 plus 72 kilonewton meter. What about M? Oh, sorry, this is 96 minus, so this is plus and this is minus. MCB is 0, obviously. Okay, so we have found out what is MAB, MBC, MBA. So once you find out the moments, it is easy to find out the shear forces. So let me just draw the beam. This is beam A, AB. I have a UDL of 2 kilonewton meter coming here, and I also have a beam BC, the same. So I have a point load of, how much is the point load? 12 kilonewtons. So MAB is minus a 108. So what is minus means? Minus is positive is clockwise and minus is anti-clockwise. So it is 108 kilonewtons. And MBA is plus 72, that is clockwise 72. Now MBC is minus, again this is anti-clockwise 72. MCB is 0. Now how do we find the shear forces? So we have this shear force. I'll just find out shear force at A. So rest I'll just note down because I already solved for it. So shear force at A can be found out as, I'll take moment at B as 0. Okay. So if I take moment at B as 0, so I have VA times 24 minus 108 minus 224 times 12. You have one more thing left, which is 72. 72 is again plus 72 equal to 0. So this is going to give V as 25.5 kilonewtons. Okay. So VA is 25.5 kilonewtons. So now in order to balance this vertical force, VB should be 22.5 kilonewtons. Similarly, V at B. The shear force here is 15 kilonewtons, and shear force here it is, this is downwards. Okay, here it is downwards because it is downwards, right? 15 minus 2, that is 3. So again, I think you might be you might be thinking, why is B not actually having an opposite 22.5 load there, right? Because if you actually find the net force here, the net force at this section is again 15. Okay, so you have 22 coming because of this, and you also have 22 plus 22.5 and 25.2. So it should also have the equilibrium that has been made, that is still that has to be maintained in the what is it, the support CB. Okay, sorry, the support, the span BC. So this is my bending moments and the shear forces in the spans AB and BC. So I'll just try to draw the bending moment and shear force diagram. So I'll just try to draw a baseline. So I'll try to draw a baseline here, and so at one support it is 108, 108, and at the other support it is 72. So it is 72. So there is a double curvature happening in this beam. Okay, this is one thing. And what about in BC? In BC, there is a point load which is at the mid span, and after that there's no load, right? So it is actually linearly varying. So you have a linear variation, something like this, and then you have something like this. Okay, so this is 108, this is 72. So you can find out what is this, and this is 0. This is hogging, and this is hogging, and there is some part which is sagging inside the beam. So hogging and sagging, these are bending moment. This is bending moment diagram. So the shear force is quite straightforward. So you have the baseline, and you have 25.5 here. So this is 25.5, and you have a UDL, right? So UDL actually gives you a shear force which is uniformly varying. So you have, so you have 22.5 here and then 15 there, right? So it has to be something like this. Okay, and then this is 15. There is uniform load up to the point load, and then at the point load you have 12. So this should be 12, and at support A there should be 3. So this is my shear force diagram. Let me just label it. This is 25.5. Sorry, 25.5, and this is 22.5, and this is 15, and this is 13. Sorry, this is 12, and this is 3. Okay, this is my shear force diagram. So this is how we make use of the slope deflection equations to find out the support reactions, as well as, and also to draw the bending moment diagram and shear force diagram for statically indeterminate structures. So any clarification or any doubts you have in this?
No.
Yeah, okay, thank you. So let us continue this, and we'll take one more one question on the frames, which are actually again where we actually make use of this slope deflection equations, and I personally feel that this makes the slope deflection equations when if we are using it on the frames, it will actually give us uh, a little quicker or little quick results when compared to any other analysis methods so far, which we have. I'm not talking about the stiffness method, and I'm not talking about the fine element methods, which are again which you'll be learning um, in the coming sessions or in the next level. But so far, whatever we have assumed, right? So I personally believe that this will actually give you a pretty quick solutions for this type of question. So again, for the frames, we have two different types of frames. One is the frame, one is a sway frame, and one is non-sway. So for the sway frame, sway is actually having a horizontal sway, so it will have a horizontal displacement. For the non-sway, there is no horizontal displacement. Maybe see, there cannot be any horizontal displacement. That is not possible. But when we say it is non-sway, that means there is something restrained which is in horizontal direction. So let us take one sway frame directly to actually analyze the to analyze. um to analyze again to analyze to find out the support reactions, and also to draw BMD and SFD. So we have a question. Sorry, let me draw it in black. So this is problem 2. Problem 2. So this is again a simple single base frame. Okay. Fixed at both ends. Okay. Also, there is an added complexity. There is one hinge. There is a hinge at this support. Okay. There is a hinge here, and let us apply a horizontal force of 10 kilonewton at this point. This is A, B, C, D. The dimensions are as follows. So this is 3 meters, and this is 4 meters. Okay, and what else? Okay, EI is constant. So in our most of the course, we usually take EI as constant, but you need to take consider this. This is there is a hinge here. Okay, this is a hinge. So what actually happens at the hinge? You have moments there, zero, right? And also there is one more important point at the hinge. So usually at the rigid joint, what we assume or what happens at the rigid joint, usually we say that the rotations actually is always the rotation after the deformation and before the deformations are or the angle between subtended between both the joint is actually the same. That's what we call it as, right? So uh, normally we take vertical and horizontal which is meeting at a 90-degree angle, so we usually say it as 90 degrees. But what if it is not 90 degrees? If sometimes we have a frames which are something like this, so this is not 90 degrees. Even then, in this case, when it is rotate, when this is bent like this, right? So this will also bend in such a way that the angle is maintained. So this angle is going to maintain. So if this is going to like this, and let us say this is 90 degrees, so we have this is 90, so this is going to bend something like this. Okay, so this angle is always maintained. Okay, so in a simply supported beam, or in a sorry, not in a simply supported beam, in a frame where if you have a hinge there, right, this is not valid there. So you see, what does this mean? So at this support, at this sorry at this rigid joint B, theta BA and theta BC are equal. That is because of that being equal, we call it as the angle is maintained, or the 90 degrees angle is maintained. But it is not so at theta C, or it is not so at the joint C. So at joint C, theta CB is not equal to theta CD. Okay. So now how is this going to deform? Let us just draw an approximate shape of the approximate deformed shape. So this is going to deform something like this. Okay. And so this is going to deform like this, and this is going to deform like this. Okay. uh, Maybe it visibly okay, this is delta and this is also delta. May I have, this is again not to the scale, maybe I have shown this length, this displacement little not equal, but please assume it as the displacements delta are both equal. So that is one thing. And again, what happens to theta? So let me say this is my theta a, again theta a is 0, this is something like this, and uh, you have, let us say this is theta ba, this is theta bc. Okay. And this is theta cb. Okay. And this is theta cd, and you have this. So what happens at the hinge joint is theta cb is not equal to theta cd. Okay, that is one point. And also the moment at the hinge joint is always 0. Okay, it is released, there's a moment release there, it can rotate. And uh, and here theta bc is equal to theta ba. That has to be kept in mind because it's a rigid uh, it's a rigid joint. So the rigid joint, the angle subtended, actually this is my angle subtended, so this is always going to be equal to the previous or undeformed shape, undeformed stage or undeformed mode. Okay. So let us start again solving this. So again, the first usually what we assume is first, again, the practice is we'll first find out what are the fixed end moments. So if you carefully observe in this, there is no fixed end moments in this, right? We are only applying the joint the forces at the joints. Okay. So there are no FEM or the fixed end moments in this question. So the fixed end moments AB, BC, BA, and CB and CD are 0, and DC again they are 0. So no need to calculate our fixed end moments in this question. So directly let us start with MAB. What is MAB? 2EI by L. So L, you need to be careful, L of AB. Okay. 2EI by L, 2 theta A plus theta B. Now we have 3 delta by L. So now you should also consider the delta. So Previously, I was telling about the support settlement, but here again the sway is again also a kind of a displacement in the support B, right? So even though I was referring it to support settlement, even if you have a sway, you have the support or the you have the point which you have considered, it is actually moving by a distance d in the vertical direction. So previously it is in vertical direction, now it is in horizontal direction. But AB is again it's vertical, right? So that is again downwards direction. If you see AB carefully, it is again in downwards direction. So that is again minus 3 delta by L, and this is going to be EI. So theta A is 0 again because theta support A is fixed support, so there is no rotation there. So theta A L is 4, so 2 by 4 it is 1 by 2. Again, this is theta B minus 3 delta by L. So mind you, I need to write here theta BC, or sorry, theta BA. But I again I said that theta BA is equal to theta B is equal to theta B. Okay, so that is the reason why I'm taking theta B here. And what about MBA? MBA is going to be 2 EI by L. So I'll write it as EI by 2 theta B minus 3 delta by L. Okay, this is one equation. And what about MBC? MBC is going to be 2 EI by L is 3 meters, 2 theta B plus theta CB. Here I'm exclusively mentioning it as theta CB because theta CB is not equal to theta B. Sorry, theta CB is not equal to theta CED. Okay, and also you need to understand that there is no support settlements or there is no sway in member BC. This is only rightward sway. So that is not giving you any added movements in that. So there is no delta term in this. This is one equation. And what about MCB? MCB is going to be 2 EI by 3, 2 theta CB plus theta B. Okay. And MCD is going to be, so again EI by 2 EI by 4, so EI by 2, I'll write it directly, 2 EI by 2. CD, so CD is 2 theta CD minus 3 delta. So you have again this is a rightward sway, right? So it is again positive. So downwards positive. So if you consider DA, it's going in downwards direction. So this is positive, and MDC is EI by 2 theta. Sorry, it's not 2 theta. This is theta CD minus 3 delta by L. 2 theta DC, but theta DC is again 0. So that's why I didn't consider that. So I have I have 6 equations in this. What are my unknowns? MAB, all these are unknowns. So let me just strike out what are already known. So MCB is 0, right? MCB should be 0 because it's a hinge support, or sorry, hinged joint. So MCB is 0, and MCD is also 0. Okay, yeah, this is fine. Then what about the rest? So I have MAB 1, 2. Okay, this is gone. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we have, did I count twice? 1, 2, yeah. So 1, 2, 3, 4, 5, 6, 7, 8. We have 8 unknowns. We have 6 equations. Okay. Okay, we have 8 unknowns and 6 equations. So one equation we can have from the rigid joint B, right? So what is that? Previously we are discussing that. So M B A plus M B C is 0. So there is one more added equation. Now we have 8 unknowns and we have only 7 equations. There is one redundancy. So how do we develop another equation? So if you carefully observe, there is one horizontal force 10 kilonewtons acting, right? So we can also write using that 10 kilonewton. We can also have a force balance in horizontal direction. So force balance in horizontal direction, right? That I can write. So force balance in horizontal direction. Okay. So what is balance in horizontal direction? H, and what I'll try to do is this is HA, this is HD. HA plus HD minus 10 equal to 0. Okay. So let us finalize whether this equation is valid to consider as another equation to solve our unknowns. Let us see whether it is valid or not. Don't Let us not conclude now itself. Okay, we'll just find out what is HA plus HD minus 10 and write down some equation and see whether it is a valid equation for us to consider it as an unknown. It has a equation to actually find out the unknown equations. Okay, so how do we find HA? What is HA? So HA is nothing but, again, it's a support reaction in the horizontal direction, right? So this is I'm just this is my A, this is B. Okay, this is something like this. So what is happening in the question is something like this. You have theta here, so you already have this. So because of this, you have what you have considered is all in the clockwise direction. So this is MAB, and sorry, this is MBA. Okay, and this is my length L. So MAB and MBA, you already know what is it. MAB is like 2A by L, 2 theta A, and all so and so. So MBA is also 2A by L, 2 theta B plus theta A, and so and so. So MAB, MBA, you know, how do you find the horizontal reaction at this point A? So this has to be this way, right? So it has to be in this direction. Okay, this is HA. How much is HA? HA is going to be MAB plus MBA by L. Okay, so we'll make use of this HA in that. Okay, in the previously written in this equation, HA plus HD minus 10. Okay, so usually we call this, again, there are a lot people call in the textbook we have many authors using this as a shear equation, shear balance or shear equation, something like that. So we can also call it as a force balance in horizontal direction or force balance equations. So this is HA plus HD. So HA, now I can write HA as, so again, you can see here HA is actually in this direction. So see, we have considered it in clockwise direction, right? This is clockwise and this is clockwise. So if it is in clockwise direction, HA should be in this direction. So right now what I'm considering is HA to be in leftwards. So then what I get is minus, right? Minus MA minus MAB plus minus MAB plus MBA by L. Okay, so what happens to HA plus HD minus 10 equal to 0? So HD is also similar. HD will be MDC plus MCD by L. So yeah, this is going to be minus MAB plus MBA by 4 minus MDC plus MCD by 4 minus 10 equal to 0. So you should be, again, you're aware that MCD is 0 because it's a hinged it's a hinge joint. So this is going to give us MAB plus MBA plus MDC plus 40 equal to 0. So now this is going to be our eighth equation. Okay, so again we have let us just rewind what we have done it. So we already have MAB, MBA, and all these equations. We have eight equations. We have six equations. So we have one added equation which is compatibility, or which is actually this is nothing but MBA plus MBC. The rigid joint, it is 0. Anyways, you can also take MCB plus MCD as 0. MCD, because MCB itself is 0, so there is no point of taking it. So yeah, that is one thing. And with this added MBA plus MBC equals 0, again we are short of one extra equation. So that we have again generated by doing the force balance in the horizontal direction, which is HA plus HD. Again, we have considered HA HD in leftwards. So HA plus HD minus 10 equal to 0. So HA we have found out as MAB plus MBA by L. Similarly, we have written it as. So we have 8 equations, 8 unknowns. So again, it is easy to solve. So let me, like I'll just solve for 2, 3, maybe let me try, let me start solving it. So first equation, let me consider something which is easy. What is that? Which one is easy? Yeah, we can take this equation. In this, we already know that M MCD is 0. So if MCD is 0, this term should be 0. That means theta CD is going to be equal to 3 by 2 delta by L. Yeah, 3 by 2 delta by L. 3 by 2 delta by L. Okay, this is one equation. And we this is 3 by 2 delta by L. And we also have theta CB. With theta CB also we can do. How can we write this? Yeah, so we can take this again equal to 0. MCB is equal to 0. So MCB equal to 0, that means 2 theta CB plus theta B equal to 0. So 2 theta CB plus theta, so theta CB is going to be minus, okay, minus 2 theta CB itself, right? Or minus theta B by 2. Minus theta B by 2. Okay. This is one more equation. And MBA, let me write MBA plus MBC equal to 0. From this MBA, where is MBA? This is my MBA and this is my MBC. So in this, what we have, EI by 2. Let me write it down. Again, this again we will be making some mistakes in the calculation. 2 theta B plus, so theta A is 0, but I also have minus 3 delta by L plus, what is MBC? 2 EI by 3 theta BC, right? So 2 theta B plus theta CB. So there's no delta in this term, right? So this is 0. And this is going to solve as, this is going to be, so again theta CB, I use this equation to and substitute for theta CB. So in this, what I'll get in the end is theta B is going to be 3 by 4 delta by L. Okay. So now we have theta, where is it? Yeah, theta C in terms of delta, theta CB in terms of theta B in terms of 3 by 4 delta. So everything we can write it in one single equation. Okay. And what is the other equation? Like just now we have derived that, this equation 8. So MAB plus MBA plus MDC plus 40 is equal to 0. So from this, what we are going to get is, so let me write this. So 40 plus, okay, I'm just writing it down here. 40 plus MAB. MAB is going to be EI by 2 theta B minus 3 delta by 2. MBA we already wrote it here. EI by 2 theta B minus 3 delta by L. So theta A is 0. plus DC. What is DC? So DC is going to be uh, 2EI by, sorry, this is again 3, sorry, this is EI by 2, DC is 2 theta D plus, so theta D is 0. What am I doing? Yeah, theta DC, right? Yeah, theta CD minus 3 delta by L is 0. Okay. 40 plus EI by 2 theta B, 2 theta B. How much is that? 3 theta B minus 9 delta by L. There is one plus theta CD, but already we know theta CD is nothing but 3 by 2 delta by L equal to 0. But theta B we already have 3 by 4. So I'm just writing it down. Just I'm a little lazy to write it. So 3 times 3 is 9, 9 by 4 delta by L. Okay. So 9 by 4 delta, 9 by 4 delta by L, 9 by L delta, 3 by 2 delta by L. So everything is in delta, so we can find out delta here. So from this we can find out delta. So delta will be, how are you going to find? Yeah, in from this 9 by 4 everything, delta is going to be 60.95 by EI. Okay, this I'm just writing it down. I already calculated this. You can cross check this. So delta is again 60.95 by EI. Also, uh, so once we find found delta, so theta b we found out how, because we already have equation for that. For that, theta b is 3 by 4 delta by L. So 3 by 4 delta is going to be 60.95 EI by 4. Okay. So 11.11 by EI. So see, I think it's very so it is important for you to consider the delta which you are taking. L, this is LAB. Okay, because see, this is L. This L is nothing but this is from BA. So BA is nothing but length of AB. Okay, so this is LAB. So LAB is 4. So that is the reason why I have taken EI as 4. So it is 11.42 by EI. So we have theta B. Similarly, you can find theta CD. What is theta CD? Theta CD is 3 by 2 delta by L. 3 by 2 delta is 90.45 by L is again 4 EI. So this is something you can find it out. And theta CB is going to be, what is theta B? Minus theta B by 2. Okay. So this is minus theta B by 2 is minus 11.42 by 2 is 11.571 by EI. Okay. So what does minus means? Minus means it is actually rotating anti-clockwise. This is clockwise, this is clockwise, everything is in clockwise direction, and this is so. So far we have found out theta B, theta CD, theta CB, and also delta. So we can find out the support reactions, right? So support reactions are going to be, I'll just write down for MAB is again EI by 2 theta B minus 3 delta by L. This EI by 2 theta B is 11.42 by EI minus 3 times delta is going to be 60.95 by EI times 4, and this is going to solve as 17.1 kilonewton meter. And MBA, I'm directly writing the answers, minus 11.4 kilonewton meter. MBC is going to be 11.4 kilonewton meter. MCB is 0, obviously MCD is 0. MDC is going to be minus 11.4 kilonewton meter. Okay. So these are my support reactions. So we have obtained the support reactions. So once we have obtained the support reactions, yeah, we also have this. Anyways, we'll just find it out. So let me just write down. So this is my, sorry, this is my AB. Okay. So what I'm saying is MAB is minus 17.1. So what does minus mean? Minus is actually a anti-clockwise, right? So this is something like this. This is in this direction. This is 17.1. Okay, fine. Then BA, I'm saying it as minus again. So this is again anti-clockwise. So this is 11.4. Okay. So this is my uh, uh, oh, this is something like a double curvature. No, sorry. This is not double curvature. At support A, you have hogging moment, and at support B, you have a sagging moment. Yeah. So, anyways, this is fine. But what about the horizontal reaction? So, horizontal reaction can be found out by again we have HA, which is MBA plus MBC by L, so and so. So, let us say this is my horizontal reaction. Okay, this is HA. So, HA is going to be. I'll just erase this. HA is going to be 11.4, and this is 17.1 plus 11.4 divided by 4. How much is this? 28.5 by 4, 7.1. Oh, great. This is 7.1 kilonewtons. 4 7 28 and 1. Yeah. Uh, this is 7.1 kilonewton. Okay. All right. So, what about BC? So, this is my B and this is C. No, let us follow the same. So, I'm just drawing. Okay. This is A. This is B. So this is BC. Okay, I'm just drawing it here. This is B. This is C. So what is MBC? MBC is 11.4. 11.4 positive. That is clockwise. So clockwise is this 11.4. So MCB is obviously 0 because there is a hinge here. Okay. Uh, and MDC, we have one more, which is MDC. So I'm just drawing it here. I'm just breaking. See, I'm just breaking it down, and I'm trying to draw the free body diagrams. Okay. So this is my C and D. For C and D, what is happening? Yeah, obviously, let's see. There is no force. There's no. Okay. There's no movement there. At D, we have obtained 11.4. 11.4 means it is negative. In what does negative means? It is in anti-clockwise direction. So it is 11.4. Now we also have a shear force, right? So shear force at D, how much is it? So D, see, we can also find it by taking moments about C, and also we can also do a force equilibrium in horizontal direction, right? If it is 7.1, this should be 2.9. Okay, because there's a horizontal force at the support B coming there, right? Okay, so this is 2.9. Um, so this is two. If this is 2.9, so you should also have a force coming here as 2.9, and this will be 2.9. So this will be 2.9, and this will be 2.9, and this will be 10. This is 7.9. Oh, oh, that is good. So what does it say? So the beam BC is actually getting compressed by 2.9 kilonewtons. Okay. So again, yeah, that there is one inference which we can get it from this free body diagrams. So this is 2.9. The beam BC is actually getting compressed. So there is compression also coming in the beam, and also there is also a movement in BC. Okay, it is all this is kind of a beam column kind of a problem. Even BCV, it is a horizontal member. There is also some compression which is coming inside the beam. And it seems like there is no vertical forces coming inside, right? So I think, is it? Yeah, I think there is no vertical forces in this. So even we call it as a column, but actually there is no forces. So this is maybe one particular case in which the columns which look like the vertical members, but they are actually not taking any horizontal forces. So not taking any axial forces. But the beam, it looks like a horizontal member, but it is actually taking the axial forces, but uh, uh, it is taking the axial forces. So, anyways, that is again one of the inference which we can get it from this question. So, how do we solve? How do we draw bending moment diagram and shear force diagram? So, let me quickly draw this. So, I have BC. Okay, this is my ABC. So at AB I have 17.1. At AB I have 17.1. So let me draw. We can actually choose either way, but usually I prefer drawing it in tension side. So let me draw it in tension side. So this is hogging, and here it is sagging. So okay, this is something like this, and yeah, this is 17.1, right? So it's a little bigger. So this is going to be this. Okay, so this is 17.1. This is 17.1 and this is 11.4. Now what is happening in BC? In BC, the tension is uh, in the bottom, so there is a sagging moment. So the tension is under again below. So this is 14 and here it is 0. So this is going to be something like this. Okay, so this is again 11.4. I always make the same mistake again and again. So this is 11.4. And what is happening at CC? It is always 0 because it is an internal moment release, internal hinge. So what is happening at D? D, it is, what is it? It is again hogging. So you have, oh, what is this? Sorry. So something like this. Yeah, here it is 0. This is 11.4. Okay. So this is hogging. I'll write it as minus. Sagging, positive. This is hogging, negative. Okay. So this is my bending moment diagram. This is my this is my BMD. So shear force is again, it is pretty straightforward. So shear force diagram also. Let me draw it. Shear force diagram. So what does it say? You have a shear force of 7.1 here, and then there is a shear force of 7.1 constant, and then you have 10, right? So yeah. So what is it saying is you have a 7.4, something like this, and even here it is 7.4. So you might be asking me what is happening. Sorry, is this a rectangle or it's looking like a square trapezoid, right? Let me. Yeah. So this is my 7 point. This is my 7.1. Okay. This is my 7.1. What is happening to the unbalanced one? It is actually compressing this. Okay. There is some compression coming. So again, that is again an axial force. So I don't want to draw the axial force in this. To again, it will be confusing. So the unbalanced will be the axial force in the beam BC. And what is happening at C and D? C and D, there is 2.9 everywhere. So it is 2.9 here. 2.9 and again. Yeah. This is 2 point. This is 2.9. This is 2.9. Okay. So this is my shear force. There is no shear in This is actually very interesting. So in the columns, there is no axial forces. There is only moment coming in the columns. So you can see there is only moments in the columns. Okay, there are moments and also the axial forces. But sorry, moments and shear forces, but there is no axial force. Sorry, but in the beam there is moment as well as there is an axial force, and there is no shear force. Okay, so this is pretty interesting. So this is how the shear force and the bending moment can be formed, and with this you can also again you what all you have in a single in a single statement or in a single array of your equations. What you have done, you found out the support reactions, as well as you also found out uh, the important parameters like the support rotations or the joint rotations, and also the joint rotations, and as well as the sway, the displacement delta. Okay, so again that is one of the advantage of using this slope deflection equations. So with the slope deflection equations, you can also find out the support reactions as well as the salient points like the joint rotations, and also uh, the sway or the joint displacements. So this is about the slope deflection equations. This is what I wanted to cover in this video session. So maybe now we can if you have any doubts, we can take some doubts.